we have some random variable x, and it is known that the variance of this random variable is equal to 160. We randomly sample 40 independent and identically distributed observations of x. And we construct the sample mean, x bar, which is equal to 1 over n times by the sum of the xi's. Now, at first, we want to test the null hypothesis that the expected value is equal to 30. So how are we going to do this? Well, remember, whenever we're carrying out a statistical test, we start off by assuming the null hypothesis is true. So if h0 is true, then by the central limit theorem, which remember states that for a large enough sample, as long as the random variable x has a finite variance, the sample mean will be distributed approximately normally, with expectation equal to the expectation of x, and if the null hypothesis is true, that would be equal to 30, and variance equal to the variance of x divided by the number of observations. So the variance of x is equal to 160, so the variance of x bar is going to be equal to 160 over 40, or equal to 4. So, if we want to test this null hypothesis, we're going to need to construct a z statistic. And remember, z will be equal to x bar minus the expectation of x bar divided by the standard error of x bar, and that would be distributed normally with expectation 0 and variance 1. So substituting in our numbers, we've got that x bar is equal to 32. The expectation of x bar, if the null hypothesis is true, is 30. We divide through by the standard error of x bar, and this is the true standard error of x bar, which is the square root of the variance of x bar. So that's going to be the square root of 160 over 40, or the square root of 4, which is going to be equal to 32 minus 30 over 2, which is equal to 1. Now the critical value from the normal distribution at the 5% significance level for a two-tailed test is equal to 1.96. Since the magnitude of our test statistic is less than the critical value, we fail to reject the null hypothesis. Now, in the second part of this exercise, we're asked to test the null hypothesis that the expected value of x is equal to 35. So we're going to do exactly the same thing. We've still got 40 observations, the variance of x is still equal to 160, the sample mean is still equal to 32, so if the null hypothesis is true, again by the central limit theorem, the sample mean will be approximately normally distributed. This time, if the null hypothesis is true, the expected value would be 35, and the variance of x bar would still be 160 divided by the number of observations. So that's 160 divided by 40, which is 4. And then we can construct our z statistic, which is still equal to x bar minus the expectation of x bar divided by the standard error of x bar, which would be distributed normally with expectation 0 and variance 1, which would be equal to 32 minus the expected value. This is conditional on the null hypothesis being true, so 32 minus 35 divided through by the standard error, which is the square root of 4, which is equal to minus 3 over 2, or minus 1.5. the critical value from the normal distribution at the 5% significance level is still equal to plus or minus 1.96. Our test statistic of minus 1.5 is between plus and minus 1.96. So again, we fail to reject the null hypothesis. So we've just seen that we've tested two null hypotheses. We've tested the null hypothesis that the expectation of x is equal to 30. We've also tested the null hypothesis that the expectation of x is equal to 35. And based on this sample mean that we've got, all of the other data is remaining exactly the same. In both cases, we failed to reject the null hypothesis. So this raises the question, what other null hypotheses would we fail to reject based on this data up here? Now, in order to answer that, we need to introduce a new concept called the confidence interval.